Hello, today we want to share with you our exploration into one of the most intriguing concepts, the formation of elements and the concept of magic numbers.
Well, you might be wondering if we are qualified to give this talk. Well, to be fair with you, we're not. And that's just how science really is. It all depends on our curiosity and our hunger for knowledge. And we do not really need any proficiency or, say, a professional degree to understand science. And this is why we really like science for this main reason. And we chose this topic as we don't know that much about elements, and we wanted to convey this and share with you all the fascinating world of science.
At the time, he had claimed to have invented elements 118 and 116. This was a major scientific breakthrough. However, as other scientists began to replicate his findings, they realized they just couldn't produce this. Why couldn't they?
Well, this is Victor Nionov. He is a physicist who worked for the National Berkeley Laboratory in California. This was a really big institution back in the time, and they mainly focused on the discovery of just the nuclear physics. So what happened was that he had faked all his data, and he had fabricated a lot of detections in order to falsely claim the discovery of the elements. And basically it was like looking for a needle in a haystack, but the haystack was made out of needles because he faked so much of his work.
Alright, now if you studied chemistry at the high school level, or even the middle school level, you probably know what this is. This is just a basic atom. We zoom into this, and we go into the nucleus of this, which is packed with protons and neutrons, with its electrons orbiting outside of it. Inside the nucleus, we have powerful nuclear forces which attract and produce this stability, in spite of the high concentration of positive ions within it.
Well, this is a helium atom, and we know that helium is the second lightest element on the periodic table. It has 2 protons, 2 neutrons. And we know that protons have a positive charge, whereas neutrons have a neutral charge. So this would essentially mean that the nucleus should fall apart because like charges tend to repel each other. And after doing a few calculations, we can see that these 2 protons repel each other with a force of 20 pounds or 10 kilos, which is insane, considering the fact that a helium atom is a million times smaller than a millimeter. Well, numbers are just numbers, and it's really hard to understand what's going on here. So let's look at it this way. Imagine a proton to be the size of a tennis ball. That would basically mean that just one singular helium atom would be 60 kilometers in radius. That's almost as big as Kuala Lumpur. And this just goes to tell how empty an atom really is. Well, stability, we know that the nucleus is held together by forces. So the scientists, or the physicists behind this, gave it a really innovative term and called it the strong nuclear force. So this is what ensures the stability of the nucleus, and that's holding the protons and neutrons together.
Okay, here we have the periodic table. And if we look at periods 1 and 2, these are actually our lighter elements, which range from hydrogen to neon. And these elements are characterized by their smaller atomic numbers and their simpler atomic structures. On the other hand, we have the heavier elements, which range from iron to plutonium. These elements are characterized by their larger atomic numbers and their larger, more complex structures.
Well, bigger atoms tend to go through a special phenomenon known as alpha decay. So what is alpha decay, Justin?
Well, during this process, the atom of a nucleus emits an alpha particle. An alpha particle is essentially a helium nucleus, with 2 protons and 2 neutrons.
Let's look at an example. Uranium-235 is a really big atom. Its nucleus is filled with protons and neutrons. So over time, this leads to an instability in the nucleus, and the only way the atom can regain its stability is by ejecting some of its mass. And that's what it does by ejecting an alpha particle.
Alpha decay is like losing weight, except instead of losing fat, they lose protons and neutrons. Alpha particles are also highly energizing particles, meaning they can have many uses. One of them being in smoke detectors. They can ionize air and actually detect these smoke particles. In the formation of these heavier elements, there exists a process known as neutron capture, which initially begins with a seed nucleus. This seed nucleus is then bombarded with many neutrons, eventually forming this unstable radioactive isotope. Now, because it is unstable, it doesn't like being in this state, so it will undergo decay. Or specifically, it undergoes beta decay, whereby a proton is broken down into neutrons and electrons, leading to the formation of a stable nucleus.
Well, neutron capture can actually occur in two different processes or two different ways. First being the S process, where the S here stands for slow. This is a really slow process here, and this occurs over a prolonged period of time, say about 10,000 years or so. And this usually occurs inside red giant stars, where secondary nuclear synthesis can take place. Now, secondary nuclear synthesis might seem like a big word, but it's really not. It just means synthesis of nucleus or synthesis of atoms. Inside these stars, there is a steady flux of neutrons, and this helps in the successive transformation of elements from iron all the way to lead.
In contrast to the R process, we have the S process. Now, in contrast to the S process, we have the R process. This is a lot quicker, in actually 1 to 2 seconds, so you can actually imagine how quick that is. The R represents rapid, and this requires more extreme conditions, such as in supernovae or in emerging neutron stars. During this, immense amounts of materials are ejected, which will lead to the formation of these heavier elements. Now, have you ever wondered why some elements are more stable than others? Well, it actually comes down to these factors.
Firstly, binding energy. Now, this might seem like something that's really complicated. Well, it's not. Binding energy is essentially the glue that's holding the nucleus together. And it's measured in mega electron volts, and it's the total amount of energy that we would require to split the nucleus of its individual protons and neutrons. What this means is, the more the binding energy, the more stable the nuclei is, and the stronger the bond is. So we would require more effort to break the nucleus apart. Let's look at an example. Iron 56 is one such element that we know that has a high binding energy. It has a binding energy of 8.8 mega electron volts. So this is one of the reasons why iron 56 is at the end of all fission reactions at the start.
Now let's talk about this special concept known as magic numbers. No, not the type you pull out of a hat, but rather the special numbers of protons and neutrons that can make a nuclei more stable. These magic numbers are 2, 8, 20, 28, 50, 82, and 126. These even numbers of protons and neutrons actually are like the superheroes of our atomic world. Why? Because they're super stable.
Well, lead-208 is one such example. It is a special isotope. It has 82 protons and 126 neutrons. And like Justin said, both of these are magic numbers, which means that there's an extra level of stability. Well, to this day, even physicists really don't understand what magic numbers are. We know that there is something that's going on, but we do not have a definitive proof of what's actually going on. So, yeah, that's what magic numbers essentially mean, because you see the magic in the name. Yeah. And like I said, lead-208 is a special isotope as it has double magic numbers. And it's essentially one of the heaviest stable isotopes that we know of, and it's used in the manufacturing of solid goods such as construction material, lead-acid batteries, and even bullets.
Okay, our next big question for you. Why can't we have more than 118 elements? Actually, theoretically, we can have an infinite number of elements. However, as Shuraim already mentioned, adding more neutrons will result in more repulsion, leading to an unstable nucleus. But that isn't actually our biggest barrier. In fact, our biggest barrier is the fact that we don't have enough raw materials to produce them at this time. In 2006, during the formation of element 118, it actually required $2 million just to produce 5 of these atoms.
Well, there's another reason for this. And it's that we cannot produce so many neutrons, and the only way we produce neutrons is by smashing smaller nuclei together, which generates neutrons. And like Justin said, this process is really expensive and it requires a lot of energies. And this is one of the main factors that's stopping us from making heavier atoms.
As we come to the end of our exploration, we can conclude that we've covered the formation of elements and the intricate forces between atomic nuclei.
Well, we've talked about the highs and lows, starting from the scientific fraud and to the genuine discoveries that have been made throughout, and the intricate balance that governs the stability of an atom.
Speaking of scientific fraud, let's rewind on our friend Victor Ninov. While his false claims were damaging, they served as a reminder to us on the importance of the rigorous process and collaboration needed before any scientific breakthroughs.
Neutron capture, decay, and magic numbers have all added to our understanding of elemental formation.
While creating above any elements above 118, we know that it's completely possible. However, it's going to be challenging. And as we continue to pursue these boundaries and push our understanding,
Well, thank you all for joining us on our exploration through the heart of matter, where we talked about elemental formation. We plan on breaking the barrier of our understanding to reach infinity and beyond. Well, here's to the new discoveries that will be made in the realm of physics and chemistry. Thank you.